Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 28, 2025, just yesterday. This paper introduces a new multitask learning method that outperforms the previous state-of-the-art by about 70% on a key performance metric. The paper is titled Rep-MTL, Unleashing the Power of Representation Level Task Saliency for Multitask Learning. And the authors use a really interesting analysis to show why it works so well. The key idea is that instead of just resolving conflicts between tasks, we should manage their shared information space. This helps protect individual task learning while also promoting complementary knowledge sharing. Also, the authors shared their work on GitHub. The repository is up, and while they're still preparing the code for release, you'll currently find a great overview of the method and the benchmarks they used. They mentioned they are cleaning up the codebase, so definitely one to watch for the implementation. Alright, so to visualize this, the authors give us a great diagram comparing the old and new ways. On the left, you see traditional methods. They focus on the optimizer, either by adjusting how much each task contributes, that's loss scaling, or by directly manipulating the update directions to resolve conflicts. But their new method, Rep-MTL, shown on the right, is different. It operates directly in what's called the shared representation space. That's the internal knowledge base the model uses for all tasks. It works to preserve each task's unique signals while aligning the helpful shared information. This figure gives us a fantastic look under the hood. So an input image goes through a shared backbone, creating that shared representation we talked about. From there, the key is calculating something called task saliency, which measures how sensitive each task's goal is to changes in that shared knowledge. The Rep-MTL framework then has two main parts. First, Task-Specific Saliency Regulation, or TSR, which helps preserve each task's unique patterns to reduce interference. Second, Cross-Task Saliency Alignment, or CSA, promotes helpful sharing by aligning these saliencies, essentially treating similar patterns as positive pairs to reinforce. So how does this all perform in practice? This table lays out the results on the NYUV2 benchmark, which has 3 complex tasks for understanding indoor scenes. We see metrics like mean intersection over union or MIOU for segmentation, where higher is better, and various error metrics where lower is better. The really important columns are on the far right, delta P task and delta P metric. These summarize the average improvement over a single task baseline. Rep-MTL on the bottom row gets a delta P task score of plus 1.70, beating the previous best, DBMTL, which scored plus 1.15. Beyond just the final scores, the authors wanted to understand how their method improves the training process. This chart compares different multitask optimization, or MTO, methods using a power law exponent. You can think of this exponent as a kind of health check for the model's shared backbone. A lower value, ideally between 2 and 4, indicates more effective training. As you can see, Rep-MTL on the far right has the lowest score at 2.92, while many others are much higher. This result suggests its backbone is learning a much more balanced representation, which enables that beneficial cross-task sharing. Building on that, the authors then perform an ablation study to see what makes their method tick. An ablation study is where you test a system's components one by one to see what each part contributes. This table shows the results for the 2 main parts of Rep-MTL on the NYUV2 and Cityscapes datasets. We see that using either cross-task saliency alignment or task-specific saliency regulation alone provides some benefit, but combining them, as shown in the bottom row, gives the highest performance gain, confirming they work best together. So to wrap things up, this work on Rep-MTL really demonstrates a key insight. The secret to better multitask learning might not just be in fixing the optimizer, but in directly managing the shared representation space itself. It successfully balances task-specific needs with beneficial sharing, leading to more robust performance. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.